Hi guys, hope all is well with all of you. We're on to chapter 7 now, and I just wanted to go through some of the concepts in 7.1 Cartesian vectors with you. You should have completed the parts A and B in the vectors gizmo on explorelearning.com. So you would have discovered some of these concepts, but I just want to summarize them to make sure everyone understands them well. So in your textbook on page 360, you have read through the definitions of Cartesian vector, position vector, and unit vectors. And basically, if you remember back to chapter 6, a geometric vector was specified by a length, which represented the magnitude of the vector, and an arrowhead, which pointed in the direction of the vector. A Cartesian vector is specified by the Cartesian coordinates of its endpoints. Okay, so a position vector is just a Cartesian vector that has its starting point at the origin. So if you have a Cartesian vector that starts, oops, that's backwards, starts at the origin, then that's considered a position vector. So for example, down here on this Cartesian grid here, this vector would be a position vector because it has its tail at the origin. A unit vector is just any vector that has magnitude equal to 1. And so what that means is that we can actually turn any vector into a unit vector by dividing it by its magnitude, and I'll show you that a little bit later after we talk about how to find the magnitude for a Cartesian vector. But we also saw that there are two special unit vectors, I and j, and this notation here, the little hat, you can either just put a vector sign on top of I and j. I use this little hat, which makes it a special type of vector called a unit vector. The unit vectors, I'm just going to use a different color here. Unit vector I is along the x-axis, and it has a magnitude of 1, of course, because all of unit vectors have a magnitude of 1. And so therefore it can be written as Cartesian coordinates 1, 0. Now remember that a vector always has square brackets around it. If you write it with round brackets, then it's considered a point, not a vector. So make sure you use square brackets if you mean to write a vector. And then our unit vector j is along the y-axis, 1 unit in magnitude, and so therefore the coordinates of the vector j would be, the components of the vector j would be 0, 1. So that's another distinction I want to make. If you have a point, 1, 0, then these numbers are coordinates. If you have a vector, 1, 0, then these numbers are components of the vector. Okay, so just a little bit of distinction about the terminology. And remember that math is a language unto itself, so using the language correctly is fundamental, just as fundamental as knowing the alphabet correctly is for reading language. Unit vector notation. So one way that we can write a vector is we can simply, or actually there's a few ways, let me do this down here so it's not under unit vector notation. So we can write a vector by specifying its tail and tip coordinates, and so the vector AB goes from point A to point B, and let's just say that the components of that vector are 2, 3. Okay, that's just an example. Or we could write the vector with just one letter with the vector sign on top, and could have the same components. Remember that any vector can be moved in space parallel to itself, and as long as its magnitude and direction are not changed, then they are equivalent. So these two vectors here are equivalent vectors because they have the same components. They don't necessarily start and end in the same place, though. So this is one way to write vectors. Another way is unit vector notation. So I could take the vector A, and you saw this notation in the vectors gizmo, and instead of writing it as square brackets 2, 3, I will write it as 2i plus 3j. And what that means is that it's 2 units along the x-axis and 3 units along the y-axis are the components of that vector. So it means exactly the same thing as this vector here, just a different type of notation in terms of the unit vectors. Magnitude of a geometric vector we saw was just the length of the arrow that represents the geometric vector. For a Cartesian vector, let's take the vector a, 2, 3. To find its magnitude, and again you would have discovered this in the gizmo, in part A of the gizmo, we simply basically use Pythagorean theorem, because this vector, vector A, if it starts at the origin or wherever it starts, okay, let me fix that. That's ridiculous. You can't have a squiggly line vector. Let's try that again. Okay, so this vector A is the resultant of a vector I that goes, or sorry, not a vector I, a vector that goes 2 units along the x-axis and then another vector that goes 3 units parallel to the y-axis. Okay, so really what we're doing here when we're finding the magnitude is we're using Pythagorean theorem, right? Because this would be 2, this would be 3. And so the magnitude of the vector would be the square root of 2 squared plus 3 squared. And so in general, our formula to find the magnitude of any vector that's written as a Cartesian vector will just be the square root of the first component squared plus the square root of the second component squared. Okay, moving on to adding and subtracting Cartesian vectors. So to add and subtract, to add geometric vectors, we needed to place them tip to tail and then draw the resultant from the tail of the first to the tip of the last. If we wanted to subtract geometric vectors, we would simply turn one of the vectors around and make it a negative of itself, and then add the 2 vectors in the same way as we did originally when we add vectors. For Cartesian vectors, it's a little bit easier. So if, for example, we have a vector A, 2, 3, let's use that same one, and a vector B, -3, 6, and we want to add these vectors, so we want vector A plus vector B, then all we need to do is simply add the components, the corresponding components of the vectors. So we're going to add the 2 and the -3, because those are both first components, and we're going to add the 3 and the 6, because those are both second components, and so my vector A plus B is -1, 9. Let me go back to a different color again. Little contrast here. Scalar multiplication. Again, with geometric vectors, we saw that meant if we multiply a geometric vector by a scalar, that meant that the magnitude will change, but the direction will not change. So means the same thing here. The mechanics of doing it again are a little bit easier than with a geometric vector. So if we want to multiply vector A, for example, by scalar 5, then the vector Ka will simply be 5 times vector A. And you can think of it as doing distributive property. Basically, you multiply both components by the 5. So Ka would be 10, 15. And if our scalar is negative, then just like for a geometric vector, it will turn the vector around to the opposite direction. Okay. collinear Cartesian vectors. So if you remember collinear vectors from geometric, sorry, I just needed a drink there, from geometric vectors, then collinear vectors are any two vectors that are on the same line. Now remember that vectors can slide anywhere in space parallel to themselves and still be equivalent if they have the same magnitude. If the magnitude changes, they're still parallel, right? So as long as two vectors are parallel, they are collinear because you can slide them to be on the same line. And so what that means is that if only the magnitude changes and the direction doesn't change, then collinear vectors are just scalar multiples of each other, right? Because all we did here with the scalar multiple is we multiplied a vector by a scalar which only changes its magnitude and not its direction. So therefore collinear vectors are scalar multiples of each other. So any vector that is a scalar vector of another vector, another Cartesian vector, is collinear to that original vector. All right, last thing I want to go over here is writing a geometric vector in Cartesian form. And so I'm going to just do the example from your textbook, example 3 on page 365, where you're asked to write a force of 200 newtons at 20 degrees to the horizontal in Cartesian form. Okay, so since a Cartesian vector is specified by its horizontal and vertical components, or the components in the direction of the unit vectors I and j, we can write any geometric vector in Cartesian form by simply finding its components. And so in our live class together we did 6.5 together, where we resolved vectors into horizontal and vertical components. And so that's all you have to do here. And so vector f can be written as a Cartesian vector by simply doing the horizontal component of vector f, which would be 200 cos 20 degrees. And the reason for that is that the horizontal component is adjacent to 20 degrees. And the vertical component, so this is horizontal, this is vertical. The vertical component is across from or opposite 20 degrees, and so therefore that component can be found by doing 200 sine 20 degrees. And then you would just use your calculator and get those numbers. And so it comes to approximately 187.9 and 68.4 for this Cartesian version of this geometric vector. Okay, I'm going to do one more example, example 4 in your textbook on the same page. So let me go to the next page for this. So example 4 has a ship that's set to travel at 23 kilometers per hour relative to the water on a heading of 40 degrees and a current of 8 kilometers per hour flowing from a bearing of 160 degrees. So this is similar to the problems in chapter 6, adding applications of adding vectors. But now we're going to do it with Cartesian vectors instead of geometric vectors. So before we can proceed to do this, actually, we need to rewrite the geometric vectors as Cartesian vectors. So the ship's course is 23 kilometers per hour on a heading of 40 degrees. That's a true bearing. So let's write that as a Cartesian vector. Let's call it S. Now we need to look at what that 40 degrees really means. So on a heading of 40 degrees, or at a true bearing of 40 degrees, means 40 degrees from 0 degrees north. So this would be 40 degrees in here. So if we want to write this vector as a Cartesian vector, we actually need this angle in here, the angle to the horizontal, so that we can resolve it into components. I mean, technically we could do it. We could also do it this way. Right? We could do that. Or we could just get this angle, which is 50 degrees, and do it this way. Either way is fine, actually. So if we do it with the 50 degrees, this is 23, and so my vector, my Cartesian vector for the ship's ship's velocity relative to the water is going to be 23 cos of 50 degrees for my horizontal component and 23 sine of 50 degrees for my vertical component. And then I need to do the same for the current. So this was the ship. The current, we're told, is flowing at 8 kilometers per hour at a true bearing of 160 degrees. So again, we need to know what that looks like on the grid here, just so we can get the right angle for finding the components. So 160 degrees would be somewhere down here, with 20 degrees there to 180, because 160 goes all the way around that way. And so again, I can either use the 20 degrees to, you know what, let me draw this again just so it's more clear. I'm going to draw it over here. So this is my 8 kilometers per hour. My 20 degrees is in here, which means that this would be 70 degrees. So I can use that. Let me just make this a little bit bigger so that it's more clear. So again, I have the choice whether I want to use these components, right, to find the components, or use these ones. Doesn't really matter. The sine and cos will be switched because they're complementary angles, so they'll come out equal anyway. If you don't know what I mean by that, don't worry about it. Okay, so the current, let's call it C. Components are going to be, this is 8, so it's going to be 8 cos 70 degrees, 8 sine 70 degrees. Okay, or I'm going to do it the other way. Or you can do, if you use this triangle, it would be, for the horizontal, it would be 8 sine 20 degrees and 8 cos 20 degrees. So if you take out your calculator and calculate 8 cos 70 degrees and 8 sine 20 degrees, you'll see that they're equal. 8 cos 70 degrees is 2.74 approximately, and similarly 8 sine 20 degrees is approximately 2.74. Okay, so those are the vectors written as Cartesian vectors. I should actually put the actual numbers here. Or actually, no, I don't need to. Sorry guys, I'm a little exhausted right now. Okay, so what we do need to do though is we need to find the resultant. So we've done part A, which is write each vector as a Cartesian vector. For part B, we want to determine the resultant velocity of the ship. Okay, so if we were using geometric vectors, we would have to slide the vectors tip to tail and then find the resultant with trigonometry. But we've already found the components of each vector. So to determine the resultant, the advantage of these Cartesian vectors is all we have to do is add the components, because that's all you have to do when you add Cartesian vectors. So the resultant velocity is going to be the ship's velocity plus the velocity of the current, which was 23 cos 50 degrees, 23 sine 50 degrees for the ship's velocity as a Cartesian vector. I just double check that's what I have, yeah. And then, oh,